Hello, so my name is Miguel. I'm from Subvisual. Subvisual is a software development company from Braga, but technically we're fully remote nowadays. And I guess my job here is to explain to you what Rust is, or to entice you into Rust in 20 minutes or less. So let's get to it. So first of all, I'm going to start showing a little bit of what Rust is used for nowadays, because it's no longer just the systems language, low-level language that it started as, even though that's still one of the main focus. But as we've already seen from the index of the meetup, there's things like Tauri, which allows us to create very rich cross-platform applications. I'm not going to go into this. There's going to be a whole talk about this afterwards. Typist is also a really cool project. I mean, there's a very high chance that these are the first slides you're seeing written in Rust. Technically, it's if you know LaTeX, this is a much better version of it from the 21st century, and I'm a big fanboy of it. And there's also a really big ecosystem of CLI tools and developer tools that are essentially rewrites of existing things, but with much better features, performance, and stability, and built in record time due to some of the things I'm going to show here. And in the meantime, also something that kind of inspired me to do this talk a few months ago, or the first version of this talk, where there was a lot of discussion online. If you know this article, you maybe know what I'm talking about. Where there was a lot of debate around this time about whether types are useful, whether they're just a hindrance and stuff like that. And I found some really cool arguments and some really not so cool arguments. But essentially, and to condense 30 years of software development into 2 slides, we went from this, which is what I used to deal with in C, C++, to this, which is much more readable, but still not okay, in my opinion. And this happens, well, TypeScript, of course, improves a lot of this, but it doesn't fully solve these kinds of things. TypeScript can only go so far because it still runs JavaScript underneath. And so hopefully I can convince you that Rust is a good option for a lot of cases. So before getting into Rust, just one brief comparison. There are actually 2 kinds of typed languages. Well, there are more, but for this purpose, I'm going to focus on 2. There are what's called structural typing languages, where TypeScript fits, and other languages like OCaml, where the types of your data are defined by the shape you give them. And so you can combine different objects and with different types as long as the shape matches. So in this case, even though foo is not the same type as bar, it fits. A foo fits into a bar because it also has the X property, which is the only thing needed here. In Rust, we used what's called nominal typing, where that doesn't happen. The types are defined by the name we give them, even though the shape may be exactly the same or very close to it. They're different types, semantically speaking, so things would not compile if we try to do what was in the previous slide. There are ways to convert between types, and this conversion can even be free, or it can turn into a no-op in runtime, but it still means we need to handle those cases. And this is both, of course, there are advantages and disadvantages to this, of course. So first of all, I'm going to focus on, or the meat of this talk is me listing 4 or 5 different things of what, for me, makes Rust a good language, or in fact, my favorite language by far, where the first of all is type inference, or type inference, never really know how to pronounce this. So if you're familiar with TypeScript and a lot of other languages nowadays, you probably know what this is. So type inference is the ability for the language, the compiler, the language server, etc., to infer types without you having to explicitly write them. And this is really widely adopted nowadays. So these are 2 snippets of Rust code. We don't need to read the first one. The one below does exactly the same thing. It's what you would write if you're writing Rust. No one writes Rust like the above. But they're both equivalent, unless I made some mistake, which hopefully I didn't. And Rust is able to, actually, yeah, there is a mistake that I forgot to fix in these slides. In the first example, we're listing everywhere that this is an array of 32-bit integers, and that each element is a 32-bit integer, and so on. But because we're doing operations where we can infer the type from one step to the next, we need to do this. As long as one place is well defined, which in this case I forgot, so that's why the example below wouldn't work in isolation. But the compiler can then infer that if this is a 32-bit integer, then what comes out of the map is also a 32-bit integer, and so on. And so we rarely need to define types anywhere, with the main exception being function headers, which is where even the compiler sets a boundary. So it actually forces us to write the full type definition in a function header. And this is both to force us to document our code, because the types serve as very good documentation, and to impose a boundary on the compiler to also simplify the compilation, because the compiler now knows that anything inside a function, maybe it can try to infer the types, but it won't have to go past that, and which would get into a whole lot more complexity at the compiler. And of course, any place where there's ambiguity, like where the compiler can't detect the exact type that should fit there, if there are two or more options, then we need to be more explicit. Second, and I would guess this is the most out of the box and the most interesting thing, is memory safety, which applies. Both memory safety and type safety in Rust apply also to multi-threaded code, asynchronous code, and so on, which is a really cool thing. That's, yeah, Go and other languages do some things along those lines, but I believe Rust was the first one and by far the most powerful. So this example here, it fails to compile. I'm not sure if you all know what a reference is. Maybe people from Java and JavaScript are not familiar with that. But a reference is a pointer to some other existing piece of data. So X is a variable. R1 is a reference, in this case, that points to X. So it doesn't allocate any extra memory. It just points to that number that already exists. And then R2 is also a reference, but a mutable one. A mutable reference is a reference that allows us to change what the reference is pointing to. And this code would fail to compile because we're trying to take a non-mutable reference and a mutable reference to the same value. The compiler doesn't let us do that, because then we won't have assurances that the non-mutable version won't change, because it's supposed to be non-mutable, but then there's another reference somewhere that is mutable, especially if these two references were separated across two threads pointing to the same place. This would lead to inconsistencies, deadlocks, race conditions, all that stuff. So by definition, Rust doesn't allow us to have conflicting references to the same memory area. This can get a lot more complex. You can slice arrays into multiple different slices and mutate each slice individually, but as a brief example, this is it. And the multi-threading safety and the type safety as well, I guess, is mainly explained by these two traits. A trait is similar to an interface in other OOP languages. This is an oversimplification, but it'll do. So if something implements the send trait, that means that it's a value that is safe to send to another thread. Sorry. If it doesn't implement the send trait, then the compiler won't allow us to create a thread and send that value to that thread. A safe value to send is, for example, an atomic reference counter. A mutexis sync is not send, sorry. And then a sync is a type that is safe to share between two threads. So note that sending from one thread to another is different from sharing a value while two threads are running simultaneously. So things like atomic values, mutexes, and all that sort of stuff, you need to combine these values in order to produce values that are send and sync. And only then can you send them across those threads. And the compiler will enforce those things for you. This I think, is the key part, is this enforcement. In C, C++, you also have all these primitives. But if you can easily go around them and write code that it maybe works and maybe runs in development, but it will fail in production a year from now, Rust doesn't let you do that. It enforces very strict rules. And it kind of, in my opinion, it forces you to write better code. Thirdly, the compiler, which is probably the most powerful compiler in any programming language. And I have 3 points here, but they're very intertwined. They all kind of relate to each other. So in essence, this is just one big point. First, zero-cost abstractions, which is something very widely discussed in the Rust community. So because Rust has a very powerful compiler and a very powerful type system, it allows us to do very complex things at compile time that will translate to very safe code at runtime without having any kind of hit in runtime performance. So there's a lot of things that in scripting languages, for example, we would do additional validations or additional logic at runtime to ensure that the data fits the type that we expect or that is correct and so on. In Rust, there's a lot of instances where we can do that at compile time, ensure that the types that we're receiving are the types that we want, forcing ourselves to deal with the errors in case they aren't. And then a lot of that overhead, those verifications can get eliminated in the runtime code, which leads to much more efficient runtime code that still has the assurances because it went through the compiler and the type safety validations and so on. And this leads to the second point, which is this often used quote, if it compiles, it works, which is not something to be taken literally, but it's something that actually happens a lot in Rust. It happens in Haskell as well. I think that's where this idea came from, which is this feeling that while you're programming, you don't even need to run things to have the browser showing the output in real time and to interact with things. Maybe you're running tests, but usually you're just running the type checker. And there's a strong sense that once you get the compiler to accept your code, there's a strong likelihood that it actually works. Of course, business logic can get in the way and can still be wrong. But this is just a very strong feeling that once you write good Rust code, this actually happens. And thirdly, and kind of to drive home the other 2 points, this idea of making illegal states unrepresentable. So because we have all these powerful compile time checks, there's this strong idea of using those type checks to make sure that our code is only in our data structures are only in a state that is considered valid, and any invalid states will be rejected. There's also this idea of the type state pattern, which there's a blog post here that goes into a lot of detail and has some great examples. You can take a look later. But to illustrate this concept a bit more easily, let's imagine an enum, a type that can be in 3 different states, an account state. So an account is either active, inactive, or banned. And depending on the type, it has additional properties. So an active account has an email and a date, the last date where it was active at. And a banned account has just a reason. We delete the email, maybe for compliance reasons. And notice that the email field is not a string. It's an email. And the email is declared down here. It's a type email that wraps a string. This is what's called a new type, the thing I mentioned in the previous slide. And at runtime, this will just be a string. The fact that this is a separate type won't take up any extra space in memory. It won't do any additional logic to instantiate a string. At runtime, this will be a string. But at compile time and while I'm writing the code, I can't just instantiate this type with a string. I can actually enforce how I want this type to be created. So for example, I can enforce that a type email can only be created if I pass an email that's going to go through a regular expression to validate that it's a valid email. And therefore, I'm making it impossible anywhere in my code to instantiate an email and therefore an account state with an email that is invalid from the get-go. So again, of course, that regular expression that will still exist at runtime, but all the logic wrapping the email type and the fact that the email is just a wrapper to a string, that will be completely improvements in many areas. But in Rust, we've had this from the start. We have mainly the tool we use is Cargo, which is a tool used to do 99% of things. It's used to build our code, to build to different targets, to WebAssembly, to different operating systems, different architectures. It's used to format the code, to test codes, to run either nightly or stable, which are the 2 different release channels of Rust. It's used to run our code even in workspaces with multiple binaries being compiled. The other 5% or whatever I said before is tools like Bacon, which is just a handy tool that I usually have on my side, which is just a wrapper to all these things before and just is used to clean up the output a little bit better. And there's of course things, I actually don't remember, I don't have a slide about that, but there's things like the Rust Analyzer, which is, in my opinion, on par or even better than the TypeScript language server. There's Clippy, which is a linter that's also, it does things that I wouldn't expect a linter to be able to do before I started using it. It's actually a really, really smart project compared to linters from other languages. But okay, tips to get started. So hopefully some of this may have enticed you, at least 1 or 2 people. That will already be an achievement. But there's still a lot of foot guns when people get started in Rust. And mainly it's that they get too much into Rust. So essentially, if you're writing stuff like that thing in the first line, that foo a, which I'm not going to explain here, that could be a whole talk on its own. But if you find yourself writing that kind of stuff, that means that you probably went too far into all these Rusts, all these smart features of the compiler, and that you can probably get around with doing a much simpler version. Just compile just clone your data, just unwrap your data. Don't worry about making it the most efficient version you can do. Worry about making it work at the first time, and then with the help of Rust Analyzer and the compiler, you're going to learn a few things here and there, how you can optimize it, how you can remove a lot of those things. And once those things click, all of this will be a lot faster to do. The tooling is built in such a way that it actually helps you learn very well. And second, finally, I don't think I have time for this, according to my timer at least, but it's something that we can discuss afterwards in questions. I want to also leave time to watch the rest of the talks. But it was just a couple of pointers about some of the counter arguments usually to Rust and maybe the counter arguments to those. So thank you.
So does anyone have any questions? Thank you.
Hello.
Hello.
Congratulations. What are the different targets where you can compile some source from Rust for different computers and
different CPU architectures,
yes.
Different operating systems, compiling to WebAssembly.
There are computers for every destinations.
Sorry?
There are compilers for every destinations.
No, it's the same compiler.
Yes.
You just specify the targets.
Okay.
It probably doesn't support 100% of the targets if you go really far into history, but a lot of them.
Even application APK to upload to Play Store or something like this.
Sorry, I didn't.
You can even create application with APK with destination
For Android.
For Android.
Oh, for Androids, yes. There's a few details there. You can compile binaries that run in Android architecture. If you're trying to write GUI applications for Androids, Tauri from the third talk, I think, also has a mobile plugin. There's a lot of options, yeah.
Thank you. Thank you. Any other questions? Over there. The microphone is for the stream, by the way. It's not for everyone.
You mentioned that Rust is your most loved language, right? But before learning Rust, what was it? And a couple chain questions on that. Like, do you still love that previous language? Or was it in your scale compared to Rust? And how long did it take for you to get proficient with Rust? Like when starting from that other language that I don't know.
Okay, tricky question there. So the first time I learned Rust was 2014. Was pre 1.0 when the language was breaking every week, and I got fed up a bit. I started using it more full time around 2020 during a side project in the pandemic. My background I started as high performance computing, C, C++, CUDA. Went to work into web development, Ruby, then Elixir. Mainly those, of course, a lot of JavaScript and TypeScript along the way, and nowadays Rust. I was also always fed up with lack of types in those languages.
Thank you for the question. Any other questions? I am the sprinter here.
Thank you. Good night. Which type of this was your side project? Because as I saw, we have some specific cases or specifically we can improve our development. Like, I don't know, could you explain more about your, I don't know, side project or which project you are working right now in Rust?
So right now I'm working on a Tauri application, which has a lot of complexity to it, but maybe we can discuss that later if you want. But in my main job, I'm currently doing high performance WebSocket server and client for a protocol that I'm trying to develop. I can't really say more about that. This side project that I mentioned during pandemic was a wrapper. It was a binding to FFmpeg, the video processing library, and OpenCV, the image processing library. And I was trying to create a fake webcam in my system so that I could have Zoom, which in Linux didn't support virtual backgrounds, to support virtual backgrounds via my program. It was a stupid thing. It kind of worked, but the fan would go crazy every time I turned it on.
Okay, any other question? Oh, I should have stayed there.
Yeah, first of all, thank you for the presentation. How hard would you say that is to migrate a project that is like in mid-size, let's say, that is written in C or C++ and to go to Rust? And is it possible to have somewhat of interoperability between both languages?
With C, yes. With C++, it's a bit more tricky, but it can be done. And so for those languages, so migrating from C to Rust, it can be done by steps, because you can have bindings from Rust to C. So you can still reuse your existing code. But migrating from some other language like JavaScript to Rust, that would probably be a full rewrite.
Okay, thank you.
Final questions? All right. Thank you very much.